We all love diffusion models and how they have kind of revolutionized text to image, but a lot of them are mostly latent diffusion models. This one is not a latent diffusion model. And one of the biggest problems with pixel diffusion models is they're so expensive to train. However, this one is not expensive to train. They try to make it cheaper to train so that you can actually train these models, these pixel models. And pixel models are kind of better at certain things because they can get kind of the fine-grained detail of the image output. For example, they're better at text because text you kind of need, like, I don't know, representing text in a latent space is a lot more difficult than representing it in pixel space. So it usually is better at text, and then it does better at fine-grained detail. So pixel diffusion models they're good, but they're just very expensive to train. They basically have a procedure in here in this paper to try to make it faster, but also they find a method that uses less data and it converges faster, which is very, very interesting. So Matryoshka diffusion models, basically the idea is they train a single pixel space model. So other models, if you want to get larger images, you basically have to use an upscaler. They train a single model on 1024 by 1024 pixel. And they also just use 12 million images, which is interesting because Stable Diffusion, it originally used 2.3 billion images. And I think it uses 600 million now, something I found online. It uses a large amount, some 100 millions to billions, while this uses 12 million images, which is very surprising and very cool. And the fact, even if it's a little worse than Stable Diffusion, the fact that it can compete with 12 million images is kind of crazy. But yeah, let's get into how this works. So first, I'm going to go through basic diffusion real quick. I recorded this earlier and my mic audio wasn't working, so I have all this here. Yeah, so I'll just go through all the steps here because it's already drawn out. But basically, if you have an image here, say this image of a cat, it's at time step 0, and we'll call this x0. Now, we have this function p, and this function p is going to be a function that adds noise to our image. So p adds noise to x0, and we result in something at time x sub 1. And x sub 1 is going to be an image with a little bit of noise in it. So you can see represented by the red pixels or red dots, this is our image with a little bit of noise in it. Then we throw this through p another time, and we get an image at time step t is equal to 2, which is it just has a little bit more noise in it. And you can see the image slowly gets corrupted until we reach time step big T, which has a lot of noise in it. So this image here is essentially a full, it can be fully sampled from a Gaussian. It's basically fully Gaussian noise. And that's what you have here. So maybe big T is equal to 1,000. And this is just a discrete way of looking at this. In reality, you actually use a continuous representation. This is a kind of naive way of doing that. You don't do it using this, but it gets the idea. So if we use this function here, x at any time step t is an interpolation between the noise z, where z is sampled from a Gaussian, and your original image x sub 0. And x sub 0 will say at time step t is equal to 0, we'll have 100% of our original image, so our cat, and 0% of our noise. Now at time step big T, we're going to have 0% of our image here and 100% of the noise, so that'll be our final time step. And you can go anywhere in between. And this gives you a continuum, so maybe you can put in T is equal to 0.5 or 0.25. So this gives you a continuum, and now t is on a continuous spectrum as opposed to a discrete one, which is actually how you model this. In reality, you actually use an SDE and an ODE, where an SDE is modeled for the forward process because you don't know what noise you're going to sample from the distribution until you sample it. But once you've sampled that noise, since you already know what noise you have sampled, you can deterministically use an ODE to reverse the process. Now, to reverse the process, you use a model. The model, we'll call it Q theta, is going to take in an image at some time step t. So here's an example. We take this image in here, and the model is going to produce an image at a previous time step, so this image here. And given this image here, the model is going to produce the previous time step, this image here. So we do that by giving the model a noisy image. We give it the time step, so this would be time step t is equal to 1, and it gives us the noise at that time step. So it doesn't give us the image, it gives us the noise at that time step, and this is just useful for stable prediction. We then use the mean squared error between the predicted noise and the actual noise in the image. So basically just reconstruction error, your normal MSE loss between your input and your output. So basically how good is it at predicting the noise? That's what you optimize. Yeah, and you can give it text as well. That you just condition it on text using attention modules. If you're interested in more about how this whole process works, there's look at Stable Diffusion, because that's basically the big model that does all this conditioning and stuff. But yeah, and then the way you sample this is you give it your noise. This would be time step t is equal to 1000, which equals big T, which is essentially, so this is x sub t, which is equal to z, which is sampled from a Gaussian, 0, 1. So you sample from a Gaussian distribution, you then throw this through the model, and the model predicts time step t minus 1. You then throw this through the model again, and then it will give you time step t minus 2. And then you keep on doing this until you get your output image. And like I said, in reality, you're not going to do this. You're going to use a ODE solver to do this for you. You're not going to do it. You're not going to do it like this. So yeah, that's diffusion. And basically, if you give it enough images, then you will have if you train it on enough images, then it will figure out how the denoising process works for a lot of different types of images, and you get something like Stable Diffusion or DALI. Now, what is the model? This is Q theta here, Q theta. Now, our model basically takes in an image and it produces noise, or it gives us the noise. Basically, we want to remove the cat from the image, and we do this using a U-Net. So the U-Net takes in this image. Let's say it's of shape height by width by 3 channels, and then we throw this through some convolutional block. So this is a convolutional neural network, and we throw it through a convolutional block. We then downsample the image, and after you downsample it, you get out h over 2 and w over 2. So basically, you've compressed your image by a factor of 2, but you've also increased the number of features you have. Let's say to 128. That is not an 8. That is now an 8. So you decrease your image size, the spatial size, but you increase the number of features you have. You then throw this through another block, and then you downsample again, and you get an even smaller spatial size, but you get a larger set of features. You then have some middle block, and then you upsample, and after upsampling, you take the features before the middle block, so before on the left side of the U-Net, and concatenate them or add them to these upsampled features. Yeah, so after that, after you concatenate them, you then throw this through another block, upsample again, and then you get out a image of shape h by w. You then concatenate the features from the first block, the first set of blocks, and then you concatenate them, throw it through another block, and you get out your output, which is the noise prediction. So that's a U-Net. Basically, if you know autoencoders, it's similar to that, but with skip connections in a way. Yeah, that's the idea. Basically, you're compressing the image, getting the features out and then uncompressing it and adding the high-level information so that it can use that. So that's the idea of a UNet, and they basically change what the UNet is doing in a way. So yeah, let's check out what they do. So let me erase this here. So given a image, say this image here, they want to, so a normal UNet would take this image in, you would noise it to some level. So maybe this image is of shape 1024 or a normal diffusion model. You'd noise it and it would predict all the noise to give you this image here. Or yeah, so that's all a normal diffusion model does. But in this case, what they want to do is they want to downsample this image, say to size 512 or 256, and they want the model, the same exact model, with the same exact parameters, to model images of varying resolutions. So resolutions of, say, 1024, 512, and 256. Basically, the model is going to process all three of these resolutions. And notice how the model does the exact same prediction. So in this case, it would predict maybe this image here at the previous time step, but they're at different resolutions. So it's predicting the previous time step, unnoising the image, using the same model, but at different resolutions. And they also use varying noise schedulers for each resolution. So maybe at this one here, maybe you have to add more noise quicker or something like that. Don't exactly know. They cite a paper, but I didn't look into that. But it looks like if you have a smaller image, you may need to add noise faster in some way. But yeah, you have varying noise schedulers for each resolution. Now, if we look down here, let me erase all of this. So if we look down here, this is our UNet. Now, basically, if we have an image of size 1024, let's kind of follow the path it takes. So this would be a downsampling block. You send it through a downsampling block, and then you send it through another downsampling block. So once you send it through a downsampling block, you get shape 512. You then send it through another one. You get out shape, say, 256. And now you have your middle blocks here. The output of your middle blocks are then sent through some upsampling blocks. So this would be 512. And then a last upsampling block, which would give you your output image or the noise predicted for that image. Now, for a resolution that is one smaller, so that would be resolution 512, we skip this first block here, and we just send it through this starting at the second block. Now, that's because this downsampled image is the same shape as this image here. So they're both 512, and it makes it easy. So you would send it through this downsampling block to get out a 256 sized image. So it would output a 256 sized image, and then it would output a 512 image, and then you stop there. You don't continue on here. And basically, this gives you two losses. This gives you L1, which is the loss for 1024. This would be a loss for X of size 1024. And it also gives you L2, which is the loss of your image of size 512. And you do the same for the smallest image, except you just do the innermost part here. And this would give you L3 for an image of size 256, like that. And this gives you three losses. And basically all you do is you do the reconstruction loss for all three of these losses. So it would be this loss plus this loss plus this loss for all images. Basically, you're training a model for these varying resolutions. So yeah, maybe at every single, like you just send in the image here, and here it has to predict the, say, the pixel or the, it wouldn't be the pixels, but it would be the noise of that part. They showed just the panda here, but it would be the noise that you're predicting. And maybe that helps it kind of extract features from the data as opposed to it having to learn those features. And in a way, this kind of acts as an upscaler, but not exactly, because these features here for the 1024 image do not have to be, they don't exactly have to be this panda here. They're probably going to be similar, but they don't have to be exactly because of the cell 2. Yeah, but basically, you're just training it on varying scales. And if we look at how the model works here, this is basically a code version of this. This is a normal unit. And a normal unit basically has these down layers, these downsampling layers. That would be this part here. It then has these middle blocks, this part here. And then it has the up blocks, this part here. And then it has the residuals, or the skip connections. Now, they use something called a nested unit. And this is a recursive function. Z, or H, is these would be your skip connections here. Z are your intermediate representations. And then O are your saved outputs for each of these losses. So it would be this one, and this one. Now, what you do is if we look at the innermost part of the recursive function, so it's recursive, basically this represents this 256 part here. So it would just represent this part here. And then if we go one up in the recursion stack, then you can see it's a downsampling block, and then you call the recursive function, which would then call this, and then you do an upsampling block. So that would represent this part here. And then you do that again and again until you get what you want, but you can go up the stack again, and you would get this outermost representation here. So that is the recursive programmatical way you would represent this. And yeah, this is just the loss here. It's just MSE at different scales. So R are your scales. You're just summing up, or you're taking the average over those scales. And you just, your resolution scales. And D, R of X is just your downsampled image at resolution R. And this is just your prediction for the noise, or in this case, it would be the prediction of the image, but you would actually predict the noise. Yeah, but that's all you're doing. You're just predicting at multiple scales, and you skip blocks. And it surprisingly works a lot better than you would think it would. So if we look here, they have, so a lower FID is better, a higher clip score is better. If you look here, it has a lower FID than the other models, like latent diffusion would be stable diffusion. And it also converges faster. And those are the two big things here. It converges a lot faster, but it also ends in a lower FID score or higher clip score. If we look at the clip score, it has a higher clip score, and it converges a lot faster. See, like at this point here, it basically beats the other ones almost in like no time, basically. Yeah, so those are some of the results. Oh yeah, and if you're curious for what the resolutions would be, they have varying resolutions. For the biggest model, it's 1024, 512, 256, 128, and 64. So 64 would be the innermost block, and 1024 would be the outermost. And they train on all these resolutions, so it's a pretty large unit. Yeah, and they have some results down here. So if you train without the intermediate 128 representation and only the 256-64, so you basically only have two resolutions as opposed to one. Two resolutions does worse than three resolutions. So as you increase the number of resolutions, it converges faster and performs better. So that's interesting. Maybe that is because you add more parameters, or maybe that is because the more resolutions you add, the better it does. That's probably something that would be interesting to kind of experiment with. Finally, here you can see it's better at text. Pixel diffusion models. Better at text. But finally, if we look here, basically they have this video diffusion model, and you just stack the frames. I think they use 16 frames. So you just stack them, but instead of just compressing in the spatial dimension, so spatial compression, you also compress in time, it looks like. So this is one frame here, and that's a compression in time because it went from 4 to 1. So that's interesting. The resolution changes not only with scale, or not only with the spatial scale, but also with time. It would be interesting to look at kind of how this model actually performs by playing around with it. But I think they open sourced it, so it'd be cool to look at. But the results all look good. So it'll be. I'm very curious to see how this performs, especially because it was only trained on 12 million images. So it'll be very, very interesting. Additionally, to train this even faster, they train. Here we go. They have a progressive training schedule that starts by training a low-resolution diffusion model and gradually adds high-resolution inputs and outputs. So as training continues, you start off with a very low-resolution images, so that would be like 256, and then you continually add larger and larger images. So you just start with this innermost block here, and after you get to a certain time step, you would add this block here. So you would add the larger resolution, and then you increase to a larger resolution. And they find maybe that helps it converge so really fast, a lot faster than the other ones because it's just training here. But also, because you're not training on the larger scales, the training speed is faster as well, and it requires less GPU memory usage, which is very nice. But yeah, that's the paper. It's very simple. Just adding more resolution seems to do better for pixel diffusion, and it increases performance just on varying performance measures.